Hello, everyone. Welcome to the first student presentation session of the S.Q.U.I.D conference. These students from a bunch of different universities have put in a lot of work into their presentations and the work they're presenting. So it's really exciting to see that work pay off. The session will have, I believe, 5 presentations from 4 different universities. And it'll cover a pretty wide variety of topics, so this is exciting. Our first presentation is from IzTech. It's Özgür from IzTech, and he'll be talking about quantum key distribution. So why don't you go ahead and get started?
Okay, thank you. I'm sharing my screen now.
Go for it.
Okay, hello everyone. My name is Öztürk. I'm studying photonics at Izmir Institute of Technology. Now I'm going to talk about the work we have done in nanophotonics and quantum optics laboratory. The title of the work is the long distance free space quantum key distribution using weak coherent pulses. I divided my presentation into 3 parts: introduction, experiment, and conclusion, and future work. In introduction, I will talk about the general Q.U.I.D systems and the quantum channel options. In experiment part, I will talk about our motivation, the challenges we faced, and the setup. I want to mention that we created basically 2 setups. First one just to test the beam expander free space optics, and later then we implement this beam expander to complete Q.U.I.D setup, and we conducted 2 experiments for 2 distances for 32 meter and 130 meter distances. Now move to introduction. So we can categorize quantum key distributions in 2 categories. In our experiment, we used B92 protocol, which is prepare and measure protocol. In this type of protocols, transmitter party, which is Alice, creates bits and sends in different bases through a quantum channel. At the receiver party, Bob receives these signals and measures the incoming signals in random basis. After this operation, they communicate with authenticated classical channel and compare their bases. And after key shifting and privacy amplification procedures, they calculate the errors. So I want to emphasize that the importance of light source. This is the most crucial part of Q.U.I.D system. For achieving ultimate security, we need single photons. Actually, we can obtain single photons from quantum dots or quantum emitters such as hexagonal boron nitride, and there are weak coherent states, which is obtained from attenuated laser pulses. In our experiment, we used weak coherent states just to, it's an intermediate step to our main goal. But this weak coherent states has a security flow that in each pulse there's a probability to be a 1 photon, no photon, or more than 1 photon. So in this case, an eavesdropper can get in the middle and process a photon number splitting attack, which if in a single pulse there are more than one photons present, eavesdropper can measure the signals and send the bob, but in single photons, due to principles of quantum mechanics, if eavesdropper tries to measure just a single photon, eavesdropper cannot clone and send to bob and create another identical state. So we have two options for quantum channel. One is optical fiber and the other one is free space. Optical, as you can see from the table, optical fibers provide high stability and low flexibility. And there are optical fiber based Q.U.I.D systems reaches hundreds of kilometer lengths, and they are commercially available. But on the other hand, free space channel is still in development, and they're on contrary to optical fibers, free space has low stability and high flexibility, and they reach to up to kilometers range. So I move to experiment part. So actually our ultimate goal is to develop a single photon based quantum key distribution system. Just for just the intermediate step, we just wanted to study and observe the optical turbulence present in propagation medium in order to use free space channel. So by doing this experiment, we just want to study the turbulence effects and how to avoid and solve this problem. So challenges. The main challenges, as I said previously, the atmospheric and optical turbulences caused by propagation medium. And the other very important problem is mechanics stabilization. In our experiment, we didn't have any automated system. So at each party, transmitter and at the receiver, we calibrated, aligned the optics by hand. It was very difficult. So the losses, atmospheric extinction, mostly caused by absorption and scattering processes, which are they are wavelength dependent transmission losses. And in experiment, we choose, actually we tried to choose respectively dry weather and minimal wind to prevent these type of losses. And then optical turbulence, the main problem is beam wandering. Beam wandering is the random displacement of maximum hotspot at the receiver location. And there are various theories to approximate the beam wandering. This is the weak fluctuation theory. And we can approximate the average radial variance in this expression R square sub C by this reduced expression. In this expression, Cn square is the refractive index structure parameter. It's a measure of strength of the optical turbulence. This parameter can be calculated, obtained by the temperature measurements at precise locations, but we couldn't do such a measurement. In the expression, the L is the propagation distance, W0 is beam radius, and we can approximate this big fluctuation like that. So, as I mentioned earlier, to transmit our signal through free space, we need to expand the incoming signal, and at the BOP party, we need to collect the signal. So we used a beam expander, and we have two options for beam expanders: Keplerian and Galilean configuration. Just to test the beam expanders, this is not a QKD system, just there's in transmitter part a helium neon laser is coupled to fiber, and it's expanded by a Galilean configuration, and the distance is 7.86 meters. And beam reducer collects the beam, and we measured the intensities with power meter. And to calculate the losses coming from optical components, we measured the powers at after every component while building the setup. This is the photo of the the short range setup. So this is our actual QKD setup. First, we tested it inside the physics building for 32 meters. I just want to explain this schematic here. We have a diode laser, and it's coupled to a polarization maintaining fiber. And so we used B92 protocol, and we encoded the bits by electro-optic modulator to polarization of the beam. And from that, we have, as a beam expander, we have Galilean configuration. After that, to specially filter the signal, we used Keplerian configuration. And after that, using a beam splitter, we got two non-orthogonal states. We made the measurements using avalanche photodiode. And this HVA is a high voltage amplifier to drive electro-optic modulator. This is a laser controller, and it's the pulse generator. We use synchronized pulse generator with laser to create random bit strings, which is not random. I'm sorry, I'm correcting. We used pulse generator to create the bits. So this is the photo of it's 130 meters between two buildings. This is the physics department, and this is the building where our lectures held. It's approximately 130 meters. And this is the photo of Alice and Bob. It's the electronics. I'm sorry, optics. So now I'm moving to conclusion. as a result, for 32 meters, we got 5.20% quantum bit error rate, and 130 meters got 2.87% quantum bit error rate. I just want to point out that for 32 meters, we had a chance to do multiple, more than, I think, 3 or 4 measurements. But for 130 meter case, for a couple of weeks, we had to prepare the setup, and alignments take a long time. We had this measurement for 130 meters. So in the future, as I said earlier, our main goal is to implement single photon-based QKD. And we want to increase the distance to 5.5 kilometers. So this is the end of my presentation. Thank you for listening to me, and thank you for your time. These are the references.
All right, thank you so much. Let's take just a couple questions.
Okay.
And then we'll keep going. Does anyone have questions? Okay, I actually have one. What was the alignment process like between two buildings? That sounds like a pain. I was just wondering how you actually managed to do that.
Yes, it was a huge pain. Actually, first, in our lab, we with polarization sweep measurement, we aligned the transmitter components in this breadboard. Then in the lab, we also prepared the receiver party, and in the lab we so for a short range we tested it, but right after we go out the lab, the alignment is gone. So at every night, we done the experiments at night. Before the measurements, it took hours of work to align the optics. And we were able to see the beam wandering effect. This laser beam were fluctuating significantly. We were able to see it with our eyes. So that's it.
Any other questions? Okay, if anyone has questions, Özgür, if you'd like to, you can drop your Discord tag in the chat and people can ask over Discord. But for now, thank you so much, and we can move on.
Thank you.
Yeah. So our next presenter is Amir Mohammadi from Princeton. He's going to be talking about topological quantum computing. So that should be really cool. Go ahead, Amir.
Okay, yeah, thank you. Let me share my screen. All right, I hope everybody can see this. Okay. Okay. So yeah, hi everybody. My name is Amir. I'm from Princeton, and I'm going to be talking about topological quantum computation, which has a bit of a bad rap in physics because it seems, I guess it's like fusion, where like it's always like hyped up, but experimentally it's like kind of hard to achieve, and there's been some negative backlash. There's been some backlash in recent times with some experimental results, notably from Delft. But I kind of want to steer away from that and talk about a different implementation of it using bilayer graphene. which is it's really hot in the experimental community right now. Okay, so okay, this is a quantum information talk though. So before I get into all of that, I want to give an introduction to topological quantum computation. So it's really all about phase of a particle. So a particle has phase. Phase is kind of useful. If it's a global phase, it's not useful because phase is kind of like it's called a U1 gauge field, which just means like it's a redundancy in the math. Unless you have multiple particles and they have a different phase, then it actually becomes important and you can measure it. So for instance, in the Aharonov-Bohm effect, you have, which is like, it's just a really cool physics thing by itself. You have magnetic flux pictured here, and then you have particles winding around it or doing something around it, and even if they don't come in contact with the flux, their phase changes and you can measure it. That's because of the magnetic vector potential. So yeah, so I mean, the point of this is phase is important and it's related to geometry. So, okay, another preliminary, adiabatic theorem. So this is like a very fundamental theorem of quantum mechanics. So it says if you have, say, two eigenstates of a system and you start in one of them, say you start down here in 0, and then you have like some classical parameter like x, it says basically that if you vary x very slowly or adiabatically, then your eigenstate will remain an eigenstate, but it'll obtain a phase. So, I mean, essentially it's saying it won't jump to 1. If you change x very slowly, it'll kind of stay along this bottom line and it won't jump. You can also achieve the requirement isn't just x changes slowly. It can also be if your energy separation between the two states is really large, or if you have a really large band gap in semiconductor and condensed matter language. Okay, so now quantum statistics. So maybe if you take like a very elementary quantum class, you'll learn that there's basically two types of particles. There's bosons and fermions. Okay, why? Because they live in 3 space, so like R3 or C3. And in that space, basically, if you interchange two particles, you're restricted. You have to like when you do that twice, when you interchange two particles twice, you get the identity. That's just like a property of 3 space that you can kind of, there's a homotopy between those two braids or curves, like you can bend one into another. So you get like a plus minus 1 phase. You have to do that because the square is 1. In general, though, in other spaces, like for instance, a plane, that's not true. And so you don't get the square is 1. And in that case, you can get arbitrary phases depending on your geometry. If you just get like a phase like e to the I phi, then it's called an abelian anion because you literally just obtained a phase. But if you have like a degenerate energy manifold, like if you have an energy level with many different states in it at that same level, then in general, you get like a unitary, like an n by n unitary matrix applied to your state where n is like the dimension of the manifold. Okay, so those are abelian. So when you get a phase, it's just called an abelian anion, and non-abelian is you get like a unitary. It's called that because like non-abelian just means like they don't commute, because like unitaries in general do not commute, but like phases do commute, so they're called abelian. Okay, okay, so that's like quantum statistics 101. And okay, so if you have particles and they have like arbitrary, or they have like a set quantum statistics they follow, what happens if you bring two particles together? So that's called fusion. So you bring two particles, say A and B together, and the fusion is denoted by this multiplication symbol. And you want to think like, what am I going to get out of that? What's the statistics of the composite particle? So in general, if you bring A and B together, you could get many different particles, and this, so that's denoted C, and then this N, ABC denotes, I guess, how many ways you can fuse A and B to get C. So it's it's non-negative. So total outcomes are, this operator is commutative, and then total outcomes are associative. So this A, B, C, if I fuse A and B first, it's the same as fusing, if I fuse A and B and then C, it's the same as B and C and then A. But the intermediate particles are not identical, like A and B is not equal to B and C. And you can observe that. So I guess in some way that's, well, okay, no, that's not a redundancy in the math, because you can actually observe that and you can use that to encode information. Okay, so like a very basic example of this is like, you have like the vacuum state, which is no particle. You have an electron, and then you have like its antiparticle. And then when you fuse the electron and its anti-electron, the positron, you get the vacuum. So that's like a fusion rule, like, you know, electron times positron equals 1. Okay, you might be confused why you get a sum. It's actually it's not that hard to realize why you could get many different things. It's just like if you have like 2 electrons and then you consider their composite system, it's not one spin. Like spin 1/2 tensor spin 1/2 can give you many different spins. Like it can give you 0 or 1, depending on like the state those electrons were in at the beginning. Okay, so an example of this is called Ising Anions. So it's very basic. It's 3 particles, the vacuum, Ising Anion, and a fermion. So Ising Anions, they're interesting because it's kind of like the simplest useful anion model. Useful as in like for computation. And okay, so you find Ising Anion. This isn't just like some random symbols I wrote down. This is actually, it comes from a model called the Kshitij honeycomb model, which I won't get into, but it's in the citations at the end. So, okay, so this is all self-explanatory, except this one is kind of interesting. So you have this sigma times sigma, can give you a 1, or it can give you a fermion. There's an or there. The plus doesn't mean you get both. And this is crucial for computation, like the fact that there's a possibility. So like there's an in-between outcome, like there's an intermediate outcome, like you could get a 1 or a psi, and you can encode information in that. So braiding, right, which is what topological computation is, you always think about. It's denoted by a bunch of matrices. Like the matrices describe how you can braid things. But I'm not really going to get into that. So I'm just going to get into the encoding first. So first you have a 1. So you start off with a vacuum state. And then so 1 times 1 equals 1. So you can split that up into 2 vacuum states. And then each one of these ones you can split up into a sigma using this first anion rule. And so you get 4 sigmas. Like I understand this looks like nonsense right now, but like trust me, this is experimentally feasible. It's not total nonsense. Okay, so now you have these 4 sigmas, and now when you fuse them back together, you can get an A or B. So as in you can get a 1 or a psi. So it can't be like this A or B can either be both ones or both sides. It can't be like a 1 and a psi, because then if it's a 1 and a psi, you return to a psi, but you started at a 1. So it's like you turned a 1 into a psi, which isn't allowed. So whatever you're at here, this AB has to fuse back into a 1. Like that's a rule. So you get this 1, 1 and psi, psi. And you just encode information in this. So you have these intermediate states A and B, and you encode your 0 state as 1, 1 and your 1 state as psi, psi. That's pretty not too much there. So you can do the same thing with 2 qubits. So that's how you encode information. And then you can do computations or apply gates to them by braiding them, which changes the intermediate states. And I mean, yeah, that's it. In the Ising Anion case, you actually also need like a local gate, but that's okay. That's not the hard part. You can do like the multi-qubit gate by braiding. Yeah, and why braiding is good is because it's kind of like topologically sound in that like local perturbations can't like turn, a knot into another knot. Like, yeah, you need like a global perturbation, which isn't really much of a thing. Okay, so that's that. Here's a model. So I could have talked about Kshitij honeycomb model, which is exactly this anion, this Ising Anion model, but I want to switch it up. So graphene, it's a lattice, it's a honeycomb or like hexagonal lattice. It's 2D, it's a plane, carbon atoms, and then electrons hop around. And well, graphene gets a lot of hype for various reasons, but one reason is that the electrons behave as if they're kind of massless. In that, okay, you can compute like the energy levels of electrons in this lattice. They're just hopping around, and you get this weird thing in the bottom. So you get two energy levels, this top thing and this bottom thing. And then they meet at the vertices of the hexagonal lattice, and they make this cone figure called a Dirac cone. And electrons that swirl, so this is in momentum space. So electrons that swirl around this cone, they obtain a phase that's related to the very curvature, which is, I'm not going to get into that, but that's just like they obtain a phase by like you change the momentum adiabatically and they get a phase, but it's an abelian phase, so it's not that interesting. Bilayer graphene, on the other hand, so you have two graphene lattices now and you stack one on the other. And then you apply a magnetic field, which quantizes the energy levels. And then now you fill, I know I'm talking really fast, but like, yeah, there's a lot of material, I'm sorry. So now you fractionally fill some of these levels. So like you fractionally fill like one of these middle ones, like, or like you fill it all the way. And then the next one, like fill it however much you want. The next one, you can fill these levels, these levels are very degenerate. So they have a lot of states in them. So you might ask like, okay, what happens if these are called Landau levels, by the way. So what happens if I like fill Landau levels a certain way? Well, you get what's called the quantum Hall effect. A fractional quantum Hall effect is if you fractionally fill. So you fill every bottom Landau level and then up to a point, and then you fractionally fill that level. And you get really interesting quantum phases from this, like very interesting correlated electron behavior. So in this specific level, though, it's theorized that there are non-abelian anions, and this isn't like some nonsense that theorists came up with. Like this level was there's a lot of theory here, but this level, this nu equals 5 halves, which is saying like I fill the bottom one with spin up and down, and then the second one with like only spin up, so it's half filled, was detected in like 1987 in gallium arsenide, aluminum gallium arsenide, which is also like a 2D electron gas. That's what it makes. So it was detected a long time ago, and there's recent hype today because it's detected, or it will, it is detected, but like more directly being detected right now in bilayer graphene with a magnetic field. Well, you need a magnetic field for all this, but it's being detected in bilayer graphene, and the excitations are non-abelian anions. And it's a really cool model for topological quantum computing. We're still a long way away, but it's a cool, you don't hear about this model very often. Okay, yeah, here are my citations. Or not really citations, but like cool things you can read for yourself. These are all original papers. And then here's my notes. I have a couple like self-study papers I've written for classes and whatnot on this subject. Thank you.
All right, thank you so much. Does anyone have questions?
Yeah, I have a quick question. So if I'm remembering correctly, like Ising Anions aren't universal, right, for quantum computation. Do you know what is the like requirement for universal quantum computation using anions? Is there some requirement you have to place on the like exchange statistics?
Oh, that's a good question. I don't know I don't strictly know the requirement, but one like necessary condition is that you have this fusion channel that can break up into multiple different things. But honestly, after that, at least from my perspective, it's kind of just like calculating these matrices. Like for instance, this R, there's a couple other matrices you compute as well that tell you like how the braiding occurs, or like, what braiding gives you. And then from that, you can say something. Yeah, but yeah, Ising Anions need a local gate, like a Z or something to act on itself. And you have to do that like outside of topological quantum computing. But like that's not, so it's a toy model. But the main thing is that you have like 2-qubit or multi-qubit gates, which is like a big part of the universal gate set.
Okay, that makes sense. So looking at these, I don't know what you would call this coefficient, like an exchange matrix, you could tell whether you can like achieve arbitrary
Exactly.
control.
Yeah.
Oh, very cool.
All right, any other questions? Awesome, that was really interesting. Thank you, Amir.
Yep, thank you.
Our next presentation is from UT Austin. It's Chris Antic, Kshitij Kapoor, Thomas Leishner, and Noah Mugan, and they'll be talking about quantum complexity and black holes. So you can go ahead and share your screen and get started.
Hi, everyone. This is Quantum Complexity and Black Hole Volume, an unofficial review by Chris Antic, Kshitij Kapoor, Thomas Leishner, and Noah Mugan. So the largest open problem in physics is the issue of relating quantum field theory to general relativity. Black holes, given their incredible density, their curvature of spacetime, and their infinitesimally small singularity at their center, could demonstrate one case in which this conflict could arise. Prior to 1975, the idea that black holes could contain information was prevalent. However, it was believed that this information would remain inaccessible to outside observers. Stephen Hawking proposed in 1975 the idea of Hawking radiation, which proposed that due to various vacuum fluctuations, it would be possible that pairs of virtual particles could be created at the event horizons of black holes, such that one particle would fall into the black hole while the other would escape to infinity, meaning that the black hole would lose mass overall. As can be seen by the Penrose diagram in Figure 1, which is a graphical way to represent space-time with space being on the horizontal axis and time being on the vertical axis, after the collapsing body, the singularity at the center eventually fades into nothingness, leaving nothing but empty space. Now, given the Bekenstein-Hawking formula, which argues that the entropy of a black hole is proportional to the surface area of that black hole, it seems that a paradox arises. If black holes do evaporate away in this way, they seem to inadvertently destroy information and violate unitarity. There were several early solutions proposed in order to resolve this issue given its nature, but most solutions came with severe drawbacks. It was initially proposed that the Hawking radiation could be entangled with the information inside the black hole. However, this would violate the monogamy of entanglement, as one system, the black hole, would simultaneously be entangled with a countless amount of particles. 't Hooft and Susskind, two prominent physicists, later proposed the holographic solution, which would indicate that the 3D information inside the black hole could be represented on the 2D surface of the event horizon. As you can see in the simple artistic representation, this could be something as simple as just ones and zeros encoded on the event horizon of a black hole. Later, Juan Maldacena would expand this concept by proposing the ADS-CFT correspondence, which would analyze space-time with gravitational theory along with non-gravitational conformal field theory on the boundary of that space-time. We will discuss this in detail in a later section. Now, these theories were revolutionary, but they did not indicate how any of this encoding would work or be performed, leaving them with massive holes. Later, a collection of 4 physicists, commonly known as AMPs, proposed that the information paradox might cause physicists to give up on one of 3 fundamental physical principles: unitarity, quantum field theory, or Einstein's equivalence principle. In order to resolve this, they proposed the firewall solution, which would indicate that the Hawking radiation would be entangled with the information inside of the black hole initially, but that entanglement would instantaneously be broken, causing a high amount of energy to be released and creating a firewall at the event horizon. This was an incredibly controversial solution, as many physicists argued that this type of firewall could not simply appear out of thin air as proposed. Therefore, it seems clear that every proposed solution has come with severe drawbacks, and we need to look at black holes in a completely separate way than we have been. Recently, a bold conjecture seems to relate two completely separate fields of study: the idea of the principle of computational complexity being applied to the description of black holes under this ADS-CFT correspondence, or the CV duality. Now, before we dive deeper into black holes, in order to understand this analogy, it's important to have an understanding of what quantum circuits are. These are important because they can be used as a tool to help better understand black holes. Quantum circuits are a series of operations done on qubits. There's an example of one on the bottom right of this slide. The most basic element of data in this quantum circuit is a qubit. Qubits are the quantum counterparts of classical bits. Qubits have special properties, which makes quantum computing useful in certain applications that are unfeasible for normal computing. Unlike classical bits, qubits can have a state of either a 1, a 0, or a superposition of both states. These qubits are represented graphically by the horizontal lines. Another element of quantum circuits is the quantum gate, which are operators that can be applied to qubits that can change the state of these qubits. Quantum gates are also unitary, meaning they preserve the norm. These are the gates that you can see on the diagram. One last concept to look at is time. Graphically, time is represented from left to right in a quantum circuit diagram.
Now we can define the idea of quantum circuit complexity in the context of these circuits. Essentially, the gate complexity of a circuit is the minimum number of gates to reach some final state. In the diagram in the top right, assuming that given our set of gates, you can't complete this circuit with some fewer number of gates, it would have a complexity then of 7 gates. If we imagine the special unitary group of 2 to the k representing all possible states of a circuit with k qubits, then we can imagine the growth of complexity in a circuit as the movement of a particle in that special unitary group. As we apply gates to the circuit, we increase the complexity, and every gate that we apply causes the particle to, quote unquote, move around in the special unitary group of 2 to the k, reaching some different location with every gate that we apply to it. The total distance in the diagram that you can see in the bottom right between the initial and final state can be thought of as the computational complexity, each branch being a different gate that we apply to it.
Okay, so for ADS-CFT, one of the reasons why we use this framework is that we're trying to combine quantum circuit complexity with black holes. And before we get into that, we have to understand what is ADS or what is CFT is. And basically, ADS is one of Einstein's field equation solutions, or one of the GR descriptions of describing space in our universe. And basically, in the diagram here with the blue picture, the first part is the Minkowski space, which is 0 curvature, and then the second part is the de Sitter space, which is a positive curvature space. And then the last is the ADS that we're using for this framework, which is an anti-de Sitter space. What's special about this geometry is that with a hand wavy description is that this negative curvature can be applied to the interior geometry of a black hole with the mathematics involved with it. And also one key factor to that is that it's also a hyperbolic geometry. And basically what that means is that any information that exists inside of that interior can be encoded into this lower dimensional boundary. And basically, a few researchers in string theory, like Maldacena, use an ADS-CFT approach where they describe the GR of the ADS and combining that boundary by using quantum field theory called conformal field theory, which is CFT. And basically, pretty much the encoded information can be described in a CFT sense in that boundary. Next section. So pretty much if we have this encoded information, can we truly understand the objects that fall in? And well, basically there's 2 problems. And the first problem is that black hole interiors grow at some point until the GR ADS starts to break down. And basically a few researchers decided to maybe find some form of correspondence between the ADS and the CFT, and they tried entropy, but it started to fail. And there's also another problem where pretty much black holes are kind of like a blender of some sort, which is any information that goes in are scrambled, and pretty much the information encoded in that CFT is also scrambled and makes it information loss still. So basically, there's a theoretical physics concept called CV duality. And basically, they're trying to combine quantum complexity systems with black hole, or like a correspondence between the ADS CFT with that. So in the next session, would there be like a quantum circuit complexity that could help us understand that interior and the scrambling of that boundary?
So we need to find some trait or attribute on the boundary, which can correspond with the volume inside of the black hole. We've said that this trait may be complexity, but then we need to find some model where the complexity of that model mimics the growth of the volume in a black hole. For one, we know the black hole volume grows far beyond polynomial time, and so the complexity of our model must grow similarly. This growth is why we can't use entropy, because entropy saturates in polynomial time, and meaning that it could not account for the growth of a black hole's volume beyond that. Black hole horizons are also fast scrambling, which we will define later, but it means that whatever model we use for complexity must also be fast scrambling. One model that exhibits quantum circuit complexity, which does exhibit these traits in complexity, is that of a random quantum circuit, in which every time step, all the gates are randomly paired together by a random gate, and this circuit evolves randomly over time. First, we can cover how these random quantum circuits exhibit scrambling. Essentially, scrambling is the time required for a disturbance to one qubit to infect the whole circuit. Imagine that some outside disturbance changes the state of a certain qubit. The type of disturbance doesn't matter, but it'll just flip the qubit or change its phase or something like that. In a random quantum circuit, that qubit will interact with, after one time step, it'll interact with one other qubit. After two time steps, both those qubits will interact with other qubits, and this disturbance will propagate throughout the circuit. The scrambling time, or the time required for that disturbance to reach all qubits, is logarithmic in K, meaning that random quantum circuits are fast scrambling. Imagine that we have a quantum circuit where we know the gates that were applied to it. If we apply the Hermitian conjugates of those gates in reverse order, we might expect to undo the operations done on that circuit, thereby lowering the total complexity, because you need a minimum number of gates to reach the state you're at now. However, if while we're time reversing that circuit, some outside disturbance scrambles throughout the circuit, the states of those qubits will be fundamentally changed. And applying those Hermitian conjugate gates will no longer reduce the complexity, instead leading the circuit on a brand new path and increasing the total complexity. This is why we say that quantum circuit complexity has stable growth and unstable decreases, which actually mirrors that of entropy. It is because of this that we call this effect the second law of quantum complexity. Now we need to show that quantum complexity in these random quantum circuits grows linearly in exponential time, similar to the growth of a volume of a black hole. There have been several techniques to try and prove this. One is via counting estimation. If, like before, we imagine the special unitary group of 2 to the k as all states that the system can possibly be in, if we divide that into balls of volume epsilon, we can estimate its total volume and thus possible states, which turns out to be exponential in k, the number of qubits. Nielsen's complexity is a technique some theorists use to estimate the complexity of a given unitary. By modeling the special unitary group of 2 to the k with differential geometry, we can apply a higher cost to non-local operators and thus find the total complexity of the final unitary. While this doesn't specifically apply to random quantum circuits, we can use similar techniques of differential geometry, which are outside the scope of this presentation, to determine the approximate complexity of a random quantum circuit over time. Using these techniques, we find that the complexity of these random quantum circuits does grow linearly in exponential time, mirroring the growth of a black hole volume, just as a random quantum circuit exhibits the same scrambling techniques. As such, complexity of random quantum circuits is a very useful toy model to understand CV duality in the context of black holes.
So just as some brief concluding remarks, ADS-CFT correspondence explains the duality of quantum complexity in black hole geometry. Black holes' internal volume can grow beyond polynomial time saturation of entropy, and therefore understanding quantum complexity in random circuit models helps characterize black hole evolution. Bounding complexity in random circuits reveals the truths about behaviors of random Hamiltonians, and all of this offers insight into the feasibility of certain quantum computations. We'd like to offer our thanks to Dr. Yuxuan Zhang and Dr. Nick Hunter-Jones, who helped us with not only this presentation, but also our research paper. And these are our references.
All right, thank you for a great presentation. Does anyone have questions on this one? No questions?
I have a question. I wanted to give another people since I asked a question last time. I know there are a limited number of questions. Yeah, hi, great presentation. That was fantastic. So I have a question about the construction of random circuits. If I'm remembering, so you had what looked like just these sort of linkages between qubits, representing some interaction. I didn't know if that was a specific type of gate. In order to construct a circuit, random circuit that's a fast scrambler, do you need to sample? So for instance, if you're doing randomized tomography, usually you need some condition a set of gates has to be tomographically complete, or in order to sample from the Haar measure to get a random unitary. Is there some sort of requirement for constructing these circuits, sampling random gates?
Well, for a random quantum circuit to be truly universal, you need a universal gate set. So that'll be a Hadamard C0 and a random phase. So that is that what you're asking, or?
Okay, yeah. So you can pick a random, you can pick sort of any universal gate set and sample from that, and it'll produce a random circuit. Do the states have to be sort of infinite effective temperature at the end of the circuit? Are they randomly distributed?
I don't quite know the answer to that question. But yeah, any universal gate set will be able to approximate a state after some random time. And of course, just the choice of the gate set will determine the actual complexity at any given time, because one gate set may be able to approximate a state better than some other gate set, even if they're both universal, just at some quicker time with one.
Okay, thank you. Yes, thanks for your answer.
Okay, we also have a question in the chat, and that's how does the number of gates in a quantum circuit correspond to its computational complexity? Is it a one-to-one correspondence?
I can answer this one again. So you can't, because of what I just mentioned, how the choice of your universal gate set determines how the minimum number of gates you need to actually have one state. For example, set A may be able to reach a state in 5 gates, while set B may need 25 gates to reach the same state, just depending on what actual gates you have in your universal set. You can't have some concrete number of complexity. When I said 7 gates, that was an arbitration just based on the set that we have. But it's called random. I mean, not random, relative complexity for that reason, because you can't define the absolute complexity of a given state, because you could choose any universal gate set. But you can say that one state has a relative complexity, which is less than some other states, because most gate sets will need more gates to reach the second state.
Okay, thank you guys. That was a great presentation. Next up, we have Skylar Chen and Adam Levav from University of Maryland. We'll be talking about hybrid classical quantum transfer learning for breast cancer classification. So go ahead and screen share and yeah.
Cool, yeah, we're going to wait for Adam to share screen and then we will get started shortly. Alrighty. Now, before we start, we do, sorry.
Technical issues, all right.
Okay, yeah, before we start, we just wanted to note that we do have the QR code for the slides. So the slides are publicly available, so feel free to peruse them during and after the presentation. So my name is Skylar.
I'm Adam.
And we're here to present to you today our work on hybrid classical quantum transfer learning for breast cancer classification.
The first, why breast cancer? Well, breast cancer is an incredibly culturally significant and generally significant disease. It's the most common cancer among adult women. So it's very important we are able to treat this. And the first step in treating breast cancer is being able to detect it, particularly being able to detect it quickly. In recent years, machine learning methods have been used to automate this process. So this is our problem statement, basically. We take in as input an MRI scan of a breast, specifically in DICOM format, which is just an image format. And then we want to output whether this image contains a benign or a malignant tumor. So we have a data set of these images, specifically the curated breast imaging subset from the digital database for screening mammography. Here we have 4 sample images that are labeled as either malignant or benign. It's very difficult to tell just looking at these whether they're malignant or benign, but machine learning methods have been shown to have some effectiveness at this problem. Specifically, the type of machine learning we're talking about is a neural network. So I'll give a brief overview for those who don't know. A neural network is made out of layers, and each of those layers has functions of neurons in them. So those neurons take in a bunch of numbers as input, and then applies a weight to those inputs and a bias, and then outputs another number to the next layer. So all in all, this takes in like a bunch of numbers from the input layer, and then applies this network and then gives a number as an output. And through a process that we're not going to explain, if you have a set of data that has labels, then you can use a backpropagation to basically find the weights for all these neurons that will best fit that data set. Specifically, it'll try and minimize loss function, which is a measure of how inaccurate basically the model is. So I have a visual demonstration here. Can you see this? Confirmation? Yes? Yep. Okay, great. So here's a specific example. So here we have a bunch of data points. There's a test training data, which is the data that we'll be using for training, and there's also test data, which we use for validation, basically. We also have these neurons that each have weights associated, you can see, and they will try and classify these points into the orange and blue categories. So if we just start training, you can see there's this measure of inaccuracy. It goes down, and you can see after a bit of time, it does a quite good job at finding the boundary between the orange and blue data points. So that's great for this data set. But there are other cases, other data sets, where this model can't as effectively classify. So for this one, it will try, but you can see that it just is not capable of understanding, if you will, the pattern in the data here. So this leads to why we want to talk about quantum machine learning as opposed to classical. Just go back. Yeah. This is fine. Yeah, because theoretical results in the past have shown that it's possible to construct data sets where this quantum advantage exists, where classical machine learning can't solve this problem, but quantum can. You have a useful quote here. Quantum systems produce atypical patterns that classical systems are thought not to produce efficiently. So it's reasonable to postulate that quantum computers may outperform classical computers on machine learning tests. However, this hasn't been shown for any practical data set. In particular, concern for us, it hasn't been shown for any medical imaging data sets.
So when we're thinking about how to construct experiments for quantum machine learning, one of the realities is that we are going to be restrained or constrained by our near-term quantum devices. And so that means we cannot really train large models that take in a lot of qubits as input. And we also means that we're going to be limited in the amount of, basically the size of the model that we are able to train. So one way that we can shrink the size of the actual model that we have to train and therefore be able to fit it onto a near-term quantum computer is to use transfer learning. So with transfer learning, we're going to start out with a pre-trained network. There are several of these that have been publicly available and trained already. And these generic networks, their task is basically they are exposed to a bunch of images. They're exposed to a bunch of images and they are to label them, say ants and bees, dogs and cats, this and that. So in order to adapt this network to a specific task, what we are going to do is that we're going to place the last trainable layer of a generic network with our own trainable layer. And what this is doing is that we're going to use the pre-trained model as a feature extractor. So the feature extractor is going to understand what colors and edges and other parts of the image are, but it's not really going to be responsible for actually producing a final classification, a final label for the image. That will be the job of our new trainable layer. And it can be as large or small as we want it to be, which is great for doing it on near-term quantum devices because we can make this layer small. So that way that we can leverage the computational power of the pre-trained network while still being able to use quantum effectively for our purposes, for classification. So here's some prior work with classical transfer learning on the same Cantor dataset with essentially the same classification problem. And this is work that is currently up for publication. So what the authors do here is that they used 512 input neurons for feature extraction, and then they use a 32 neuron hidden layer for fine tuning. So their transfer model size eventually gets squashed down into 512 numbers, and their layer for actually doing the classification is 32 neurons wide. And the best result they're able to achieve is 67% accuracy, which is okay, but is not the highest accuracy in the world for a medical data set. And so we wanted to know, can we do better on this data set using quantum transfer learning? So here's our experimental question. Given a classical model and a quantum model with the same architecture, which one will have an advantage on this classification problem? So here's our model architecture in a little bit more detail. And this was heavily inspired by Penny Lane's work on quantum transfer learning. So as input, we're going to start with a DICOM image. This is the MRI image of the breast tumor. Then we're going to pass it through a pre-trained model. In our case, we're going to be using Resonant 18 and MobileNet V2 as base models. These models are really large and impossible to train on, say, a single GPU, perhaps. But someone has done all the work already, which is great for us. Now we're going to pass this result from the transfer model into a dressed quantum circuit. So the first layer in the quantum circuit is going to be a linear pre-processing layer. And this will embed the classical representation from Resonant 18 or the other transfer model into quantum space. Then after that, we're going to pass the quantum representation into our quantum circuit. This is the quantum processing unit. After the quantum circuit completes this job and we take the measurement, then we're going to do some linear processing to convert this into a probability of 0 or 1, which we're going to say, we're going to map this onto a classification of benign or malignant tumors. So the actual circuit that we're going to use is going to be a variational quantum circuit. And here's our simplified circuit design for a very tiny circuit. This circuit here has 2 qubits, and it has a circuit depth of 2. And the specific architecture was chosen because Penny Lane has showed that this was successful for other transfer learning tasks. So the way this circuit works is that we're going to be repeating layers of the C-NOT gates to achieve entanglement between the qubits. This is after we put everything to superposition with the Hadamard gates. So after each layer of entanglement gates, we're going to pass them through some RY gates, some rotation gates to rotate the quantum states in the Y basis. We're going to repeat these pairs of entanglement and rotation gates for every layer of the circuit. So circuit depth being 2 here, that means it's being repeated twice. So what's interesting about these variational quantum circuits is that they are universal function approximators. They can approximate any arbitrary function, just like classical neural networks can. So in order to have a reasonably fair comparison, we're going to compare this against a matching classical circuit, where we're going to replace the rotation gates with neurons. So the Q equals 2, D equals 2 equivalent for a classical neural network will be that we have 2 layers of 2 fully connected neurons. And so for the experimental design, we have a lot of independent variables. The most important ones are going to be comparing classical and quantum models against each other. We have some other variables too, such as the transfer model, the size of the circuit, and the training set size. And these variables are chosen to match the requirements of a low-spec, publicly available quantum computer. So all of the code was written in Python using PyTorch and Penny Lane for the machine learning layers, and everything was run on the University of Maryland's high-performance computing graphics cluster. And each model was sampled twice with 2 different seeds, and we have lots of dependent variables which are going to measure basically the quality of the model under different conditions.
There you go. First, okay, we're going to split up these models by broad categories of architecture, and then look at the Q and D, the depth and the number of qubits, to see if they actually have an impact on the quality of the model. And just looking at these graphs here, you can see that there doesn't appear to be a meaningful relationship. If we do a statistical test specifically, you can see that none of the p-values here reach significance level, which again indicates that there isn't a meaningful relationship between these variables, between the depth and length, the depth and width of the circuit, I should say, and the efficacy of the model, which is not what we would expect, right? We would expect that if you have a more complicated model, it would be able to express a broader range of situations, and thus it would be able to find a better approximation of the data set. This also suggests that we can approximate our grid search over the architecture space with basically a random sample. Because it seems that though we didn't do a random sampling, we did do a systematic sampling of the space of architectures, it doesn't actually have an effect on the quality of the architecture. So they're basically randomly sampled because they don't have any meaningful relationship here. Okay, there's an error in the animations there. Oh, yeah, I see why. So again, we consider these as a systematic sample from model space, but we can approximate that as random. So we just look at here the AURSC. It doesn't matter because these results are basically the same for all of these measures of efficacy. You can see if we look at all the classical models, all the quantum models, the quantum models have significantly higher AUROC, and also they have a much lower spread compared to classical models. Because we have pairs between the classical and quantum, we can also look at those directly. So like each of these lines here, the orange dot represents the classical model, the blue triangle represents, the blue triangle represents the classical model, the orange circle represents the quantum. Hinting that in almost every case between these pairs, the quantum model performs better than the classical, except for this one. But if we look at these differences in a histogram, you can see that it has a clear distribution above zero, so it has a mean of roughly 0.4, 0.5, which you can say that the quantum models, on average, have a 4% higher AUROC compared to the classical models. Let's see, the quantum models here perform consistently better than the classical. Can apply a statistical test to this, referencing that previous approximation of independence of samples. See that for almost all of these statistics, the p-value is significantly below standard threshold, indicating that the quantum models perform statistically better than the classical. There are some interesting things to learn here, though. You see that the recall of the classical models was not statistically significantly better. In fact, the statistics indicate that the quantum models had a lower recall, but a significantly higher precision, which then in turn led to significantly better AUROC and AUPRC, but not statistically significant higher F1. However, this apparent increase in efficacy comes at a cost, specifically a cost in training time. You look at the seconds trained here, see that the quantum models universally took more time to train than the classical, also they have a much larger spread. So in other words, on the simulator at least, you can say that the quantum training is much less efficient, because in the same amount of time it took to train these quantum models, you could have trained a classical model that had much more parameters in this, and thus would possibly, likely even, do better than the quantum model. It could also be that this is a result of the classical models not having enough time to train. For example, it could be if we gave the classical models more epochs of training, they could train more effectively, fine-tune their weights better, and then thus become a better classifier. But if we look at the accuracy and loss plots, not included here, it seems that that is not true.
So, in conclusion, we find that the examined quantum models have statistically significant increased accuracy, precision, and AURC compared to their classical counterparts. So there are some caveats to these conclusions, one of them being that this only shows advantage for these particular classical and quantum architectures. As the results from the training time has shown, it's currently probably more practical to train a classical model than to use a quantum model. However, these results are still encouraging for practical quantum machine learning algorithms, because our results suggest that there is a possibility that quantum advantage may still be observed in regular data sets. So for future work, we would like to train our models on real quantum hardware to determine if a speedup is possible given quantum hardware. And we would also like to note that empirical evaluation has limited utility for investigating quantum advantage. One is that generally the hyperparameters will explode as you add more of them. So the number of possible model combinations to consider may end up growing very quickly. And another factor is that typically evaluating classical algorithms is through empirical studies, whereas evaluating quantum machine learning algorithms is done through theoretical results. And reconciling the two together is still an ongoing task. So we would like to propose that looking into AI explainability to evaluate differences between quantum and classical machine learning models and seeing how they are explaining the results differently may provide another avenue to explore a quantum explainability advantage versus simply a quantum accuracy or other performance metric advantage. And we have references here as well as some extra data in the end of our slides for those interested, and we're happy to take questions at this time.
All right, thank you guys. Does anyone have questions? Oh, okay. There's one in the chat. Since the last time we spoke on Discord, you weren't able to achieve better accuracy in the classical model. What changes did you make to achieve your results? Also, does the use of a GPU help with training time of a VQA?
Yeah, that's a great question. So the question is, basically in our previous work that we did at our local SCU conference, we were not able to achieve a better accuracy. So the change we made this time is, one, we took more samples. In order to perform the statistical test, basically, we need to have enough samples from both classical models and quantum models in order to compare the two. So it appeared that with our smaller data set size, at least looking at it visually, when we plot all of the data points together, that the accuracy was not significantly higher. But then when we took more samples and we performed the test, then we saw that there's probably a slight increased difference. And so that is the difference there in having more data to help our statistical comparison. And does the use of a GPU help with training time of VQA? It does, because what it's optimizing is the back propagation step. So if you go back to the time slide, so the main difference that the training time is increased so much is because it's simulation on a classical computer, right? So every single permutation of the quantum states needs to be considered while running the quantum algorithm, right? And so although we do have a GPU to help accelerate the matrix calculations needed for updating the models while training, there is still the general bottleneck of being forced to use this classical simulation. And so that's one possibility of trying to test on the real hardware to see if you remove that limitation, will the training time be more comparable?
I'd also want to add something about the comparison efficacy. Previously, we were comparing to the results of Jamor, but more recently we decided to directly create a classical model which is more comparable to our classical model, to our quantum model, I should say. And that's another possible reason that we could have a more effective quantum model, because we're doing a more fair comparison between the classical and quantum models compared to previous results.
Okay. Thank you to both of you. Great presentation. Let's move on to our last presentation of this session, which is by Arjun, Bala-Mehta, Srila, Palanikumar, Regina, and Estella Zhao from University of Texas, Austin. They're going to be talking about variational quantum algorithms. So whenever you're ready, go ahead.
Can you see our screen?
Yeah, there are a couple boxes in the corners, though, on the sides. They look like the Zoom boxes, so if you could just minimize those as much as you can.
Okay, I don't think the boxes are completely gone, but we could get started. So hi everyone, our research group is going to be presenting on variational quantum algorithms and some applications of them. I'm Srila.
I'm Regina.
I'm Arjun.
And I'm Estella. So we'll start off with a basic definition of what a VQA is in the first place. Oh, I'm sorry, could you go to the next slide, please? Great, so a variational quantum algorithm, or a VQA, is a hybrid quantum classical optimization algorithm that we're able to implement in the era of noisy intermediate scale quantum computing, or otherwise known as like the NISQ era. These have benefits across many fields. For example, variational quantum eigensolvers are often used in quantum chemistry. Optimization problems like the traveling salesman problem are more easily solved by variational quantum algorithms. And finally, our topic, variational quantum linear solvers, are used for solving systems of linear equations that classical computers can't really do. So we'll first examine the quantum and classical components of the VQA itself. There's three main ones to know, which we'll go over right now. They're the cost function, the ansatz, and the optimizer. We can see here these three components. Each cycle contains both quantum components, which is the ansatz, and classical components, like the optimizer. Once we've reached an acceptable threshold for optimization through an iterative process, often after many iterations, we have our output, which is usually the answer to our problem. So we'll talk about cost functions first. Basically, a cost function is a function of various observables of a system. And for example, for the energy of a particle, examples of observables here would be as kinetic and potential energies. In the linear solver, which we'll discuss a little bit later, the observables are the mathematical values that solve our problem, but more on that later. The output of the cost function is usually a real number that measures the measure of optimization, or basically how close we are to our actual problem. This includes things like minimizing error or maximizing utility function. We want to find the perfect set of observables through our cost function, or the conditions of the system that minimize the output of the cost function. We can see the function on the screen here. C of theta is a function of rho of k, O of k, and a unitary of theta. Rho of k is going to be our training set that we use to train our models like we do in classical machine learning. O of k is going to be our observables, and U of theta is going to be a parametrized unitary, which is just a representation of our circuit. For a cost function to be desirable, there is a few conditions that it must meet. The first one is that the minimum value of your cost function has to be relevant to the problem that you're trying to solve. Second, the cost function shouldn't be easily estimatable by a classical computer, because that's the entire point of using a quantum algorithm in the first place. And finally, it should be trainable, which is where ansatz and parametrization comes in.
I think you might
Stella, I
be
think you're
muted.
muted.
I'm so sorry. I did not realize it was muted. Yeah, so in the context of a VQA, what an ansatz is the ansatz is a quantum state that is evaluated by the cost function. This quantum state is created by some quantum circuit made up of alternating parametrized unitary gates. And this circuit is what we're trying to tune so that then we can get the quantum state that we want to evaluate some computational task. So these unitary gates are dependent on the type of ansatz which may be chosen with respect to the specific computational task. So for example, there's the hardware efficient ansatz, which is one that is used specifically to reduce circuit depth in any given computation. So these unitary gates upon which the ansatz is based are tuned by some real theta parameter, which is given by the classical optimizer for each iteration. So once we pass through the quantum circuit and we're left with that quantum state, the cost function then evaluates this resulting quantum state, and the process is repeated until the cost function determines this ansatz to be optimized.
So in terms of the optimizer, this would be the classical component of the VQA. This classical computer takes in the result of the cost function and produces parameters that would theoretically decrease the cost. So if we go back to the graphic of all the components, Estella, we can see the classical component here on the bottom left of the middle portion of the graphic. So the new set of parameters that the optimizer produces is used to parameterize for the next iteration of the quantum circuit. And next, for training, gradient descent is used to train the VQA. The gradient is essentially a vector that points us in the direction of the parameter space that would, in the parameter space that would decrease the cost. So if we take a look back at the graphic on the previous slide, you can see the blue graph on the bottom right. And this is just one example of how the cost might vary with different parameter settings, but for different problems, this graph might look different. One of the dimensions of the graph is the cost, and each of the other dimensions of the graph is each of the different parameters. So technically speaking, the gradient points in the direction of steepest ascent. So the negative of the gradient would point in the direction of steepest descent. Since we're trying to minimize the cost starting at any point in the graph, we'll use the negative of the gradient to move, quote unquote, in the direction of steepest descent. This means that generally speaking, we'll adjust our parameters in the direction indicated by the negative of the gradient. One way of finding this gradient is by using analytic gradients. This method involves using the parameter shift rule this rule dictates that we should slightly shift the parameters in either direction, find the output of the quantum circuit at these values, and then perform certain arithmetic calculations to calculate the gradient. The specific format of the parameter shift equation depends on the eigenvalues of the unitary encoding the parameters. So it might be different for every problem. So on to VQLS. Moving away from a description of the overall structure of a VQA, let's talk about one specific application of VQAs, of which there are many, as previously mentioned. Linear systems of equations can be solved classic in polynomial time. Linear systems represented matrix A can be solved by the algorithm, which is a quantum algorithm. This algorithm scales logarithmically in n, linearly in kappa, and polylogarithmically in 1 over epsilon. Here, kappa is the condition number of the matrix A, epsilon is the desired precision of the solution. However, since the circuit depth is so massive for HHLs, it's impractical to use HHLs in the near term. Therefore, one possible solution is to use a VQA. Specifically, we would use a variational quantum linear solver or a VQLS.
So the way that the VQLS algorithm actually works is essentially given an n by n system of equations that can be written as the equation AX equals B, where A is your matrix, X is the vector that you're solving for, and B is your constant vector. Essentially what VQLS does is that it uses an ansatz to guess a state psi, and essentially it'll try to change its parameters until psi is as close to our desired X vector as possible. And the way it does this is that it uses our ansatz. Initially, it will randomize that psi to just a completely random psi state. Then it'll apply our A matrix that's encoded as a unitary, apply that A matrix to our psi state, and then it'll compare that to our given B vector, right? And then based on how similar those are, you can create a cost function and then minimize that cost function. And then basically the minimum cost would then correspond to a solution wherein you have a psi that's proportional to your X vector that you're solving for. Now, this cost function can be written as shown on the slides, where both the numerator and the denominator of this fraction can be pretty easily solved for with a simple circuit called the Hadamard test, which I'll briefly go into later. But essentially, that's how VQLS works. It's just estimating a psi state, comparing it, and then comparing it to a given vector, right? So if you want to go to the paper quickly. So, yeah. You could scroll up a little bit to page, or that works. So essentially, the way that you can find this actual cost by, like, if you were trying to implement this on Qiskit, for example, like using Qiskit, you could use this Hadamard test, which essentially will find the expectation value of some unitary being applied to some state psi. So if our state psi here is the state that's created by our ansatz, and our U is our unitary for our A matrix, then we can pretty easily find those expectation values that come up in our cost function. And there's a proof for all of that in the paper, but I won't go too deep into that. But essentially, yes, that's the VQLS algorithm. It's not all that complicated, but sort of the gradient aspect of it is done in the classical computer, and the overlap aspect of it using this Hadamard test is the quantum side of it. Yeah.
So in conclusion, variational quantum algorithms are one of the most useful quantum algorithms in the era of NIST computers because they're so robust to noise and they're widely applicable to a wide range of problems. Variational quantum algorithms allow us to speed up computations that would take extremely long and are extremely inefficient on classical computers, like the VQLS that we just mentioned. We're really excited to see where this kind of technology goes, and we want to thank you all for listening to our presentation. We're taking sorry. We would very much like to thank the Texas Quantum Collective for facilitating this project. And we'd also like to give special thanks to Dr. Noah Davis at UT Austin for his guidance in the later stage of this project. Yeah, thanks everyone for listening. And we are now taking questions about our work.
All right, thank you so much. Does anyone have questions? Okay, I actually have a question. It's about the optimizer you guys use. So you have talked about this gradient descent method that's obviously going to have trouble dealing with any situation where you have local minima in the cost function. Have you thought about using different optimizers? Are there any complications involved with that, or is it just kind of a drop-in? You can just swap them out at will.
Yeah, the specific optimizer it's not as like important to the problem as it is as like the other aspects of it. Certain optimizers will be excuse me, certain optimizers will be better at avoiding sort of those like slight local minimums and better at finding like the more the deeper minimum that will correspond to a better overall solution. There are actually certain gradient descent methods that are being proposed, especially for like VQLS and all that, where you can essentially find like the gradient using your circuits that you've already been using. So for example, with VQLS, you can actually take a partial derivative of the cost function plus both you can basically take a partial derivative of your cost function and find that gradient vector pretty easily. And then you can just solve that using your quantum computer. So you don't actually need to rely so much on the classical optimizers. But yeah, I'm not sure if that answered your question for me.
All right, thank you. Do we have any other questions? Okay, so that concludes our first student presentation session of S.Q.U.I.D. Thank you to everyone who presented today. You guys did a great job. Congratulations for finishing your presentations, and we hope to see you later at the rest of the presentation sessions and at the rest of our S.Q.U.I.D events. So yeah, thank you so much.
Thank you. We will continue with Regi's student panel later.